Okay, the new Zoom tells me that in a nice human voice. And then I have two topics today. Probably we will get done a little bit early today, which maybe you'll appreciate. And so the first one, we're going to talk about the exam. A lot of people have asked about the exam, and I promised to get to that as soon as I was done with lab 4. So we're going to review that. I'm not saying the exam is all done, but a lot of decisions have been made between me and our great TAs. So we'll go over that, and then we'll go over more about using FreeRTOS. I got my final glitches fixed for making sure that we can still use ISRs with all the cool features that FreeRTOS has. And so I'll do more examples of coding and demos in FreeRTOS. So that's our agenda for today. Before that, any questions, comments, or issues that you might want me to address? Okay, first of all, somebody just say good afternoon or hello so I can make sure you guys hear me.
Good afternoon.
Thank you. That means I can hear you. Thank you, Leonard. All right, and you can hear me. So without any more formalities, I'll start sharing. Okay, so looks like you should be able to see the screen, and this is the update on both the exam and the participation grade. So going into this quarter, I announced this breakdown of points for the class, and mostly we've stuck to it, but there's a couple of issues coming up that we ought to talk about. So first of all, class participation, that just isn't going to work. It's hard for you guys to participate in class, and it's hard for us to measure your participation other than the labs and so forth. So we're getting rid of those points, or let's just say those points, we're going to keep them, but redistribute them. And then the exam needs some definition and clarity. So here's what we're going to do. So this is the same syllabus or breakdown, and we're going to change these last three. So lab 4 is going to go up to 100 points instead of 80 points. And what we're going to do is, first of all, instead of just sort of magic pass fail, you're going to get 5 points for 4.1 without taking any points from the lab. In fact, those are added points. And then we're going to add 15 points more to the second part of the lab, 4.2, and increase our focus on the project. So these are extra points you get for the coolness and challenge level of your project that you successfully implement. So that's where 20 of those points go. No more class participation grade, and then we'll make the exam 50 points. So that's how we're going to do that. So the total will still be 450 points. And we resolved those two issues. So details. So we're going to do this at the official UW exam time. And that's in your My UW schedule. And it's going to be on Zoom. So you should be on Zoom at the time that you're doing it. The exam will be 2 parts, and it's not that, well, it's going to be 2 parts. They're going to be available simultaneously, so you can address them in whichever time sequence you want to. They will be turned on at 2:30 and turned off at 4:20. And there's going to be a Canvas quiz with some multiple choice questions that you answer on Canvas. And then there's going to be a written exam. And the total of these two, I expect the Canvas multiple choice quiz will be 10 to 15 points. It's not quite decided yet. And then the rest of the points will be the written exam. And the written exam will be a document with some questions. And you have multiple options for turning that in. You can take some plain paper. You could print it out and do the exam on paper. We recognize a lot of people don't have printers. So just blank paper where you fill in the title and the question numbers. Obviously, you do not need to reproduce the question. And then just write your answer and then scan those using a scanner or a scanner app on your phone. You could type your answers into a document and make that a PDF. You could, if you really want, you could handwrite on a tablet device and make a PDF. But we will not accept just taking of photos of your written work because I've tried, and the quality of those photos is really hard. It's never good enough. Even though a scanner can sometimes is sort of starting with that. And we're going to have a couple, if you've never used a scanner app on your phone, we will have a couple of tested and recommended apps that we'll send you. They're free. So that's not a big deal. And then the exam will be, you work by yourself. You will not surf or go on your internet while you're doing it. It's closed book and closed notes, but you can make a crib sheet. And that you can, from any notes, videos, materials, anything you want, you can create your crib sheet and you can use that in the exam. And then the exam topics, this is approximate but pretty close since the questions aren't written yet. C coding, you might have to write little functions or programs without running them. Microcontroller architecture, short answer or multiple choice type questions on how a processor just like ours works, what pieces it has. Ability to read and understand the data set, data sheet that we've spent a lot of time on in class. That'll be short answer or multiple choice, but you do not have to, certainly you do not have to memorize the data sheet. That is, every question will have the information excerpted for you, copied, pasted from the data sheet with attribution, of course. And then you have to answer a question about it. So definitely do not spend any time memorizing that data sheet, but reviewing the parts we've gone over and your ability to answer questions about them. Scheduling concepts and analysis, round robin, synchronization, task control blocks, preemptive scheduling, diagramming, scheduling, task execution and schedulers. And the format would be short answer and or scheduler diagramming. Serial data communication. We talked about, actually, we also talked about USB, that's in here. So don't forget USB as well. And that would be short answer or multiple choice, and also critical sections and semaphores, mostly just stuff we've talked about in lecture, and you can read about in the reading. So that's the information we have right now on the exam, which is pretty much set. And then I will also be definitely releasing study materials for the exam. So I have lots of old exams that to greater or lesser extent overlap with this material. So, in some courses where I'm teaching it every year, and this is year N+1, I just release old exams and solutions for you guys to study. This is different because I haven't taught it in 12 years and we've changed things for obvious reasons and not obvious reasons. So you won't be able to just, if you just study those exams, there will be material that's off topic. And so I'm going to figure out a way to create study material that is right on target for this exam as soon as the exam's done. So watch for that stuff. So that's really, in a nutshell, the exam part. Are there any questions about that? Okay, and I will post these slides once I correct the USB thing. Excuse me. All right, so let's go back and review a little FreeRTOS and show a few examples. Okay, so we did this task. Let's see, so we did this task. I showed it to you and we got it running. I'm going to update it a little bit. But basically we had these 3 tasks. We had an ISR to change the tasks, change one of the tasks. And then we're going to add 2 things. One is I had the liquid crystal, I'm sorry, the 7-segment display running under FreeRTOS as a task. And we had a fundamental problem, and that is that it flickered too much. Let's see, I'm going to, so we did this demonstration, and I'll come back to this demonstration, but first, actually, I don't have a slide about this experiment, so I will just go to the code. All right, so here is I think, let me make sure, could people please indicate that you can see the Arduino IDE on my screen share?
We can't actually.
You cannot. Okay, I'm going to fix that. All right, I think you can now, correct?
Yep.
Great. Okay, so right, so this is this is one of the first FreeRTOS applications that I showed you, and we had this is the same plugins. This is all details of the wiring for the 7-segment display, which was a Lab 3 thing, and I was porting that to FreeRTOS in terms of 3 tasks. Blink, which is just blinking an LED, display scan, which is driving the 7-segment display according to a 4-digit number created by some other task, and then a task counter, and the counter, of course, changes the value to be displayed. And this counter was using, this is a global pointer that points to an array. This is straightforward counting by the ++ operator. It rolls over at 999, which is nice for the display. And then this function I to Ds was converting an integer into 4 digits. And so this is an array of 4 integers between 0 and 9. And then this pointer points to the array. And then we wait for 1/4 of a second. That was a fairly fast counting speed. And this ISR was not used. I couldn't get it to work, actually. And I finally figured it out. And it taught me something that'll help you and maybe save you guys some time. So in our display scan, we're looping through we're running continuously while one. We are, I'll kind of move my head a little over. We are lighting up the digits one at a time. And then we figure out, this is our array of 0 to 9 values for each digit. So the dval is the number that we're going to display in the current position. We convert that to segments, which is just a lookup table. There's no algorithm to get the segments for a 7, for example. We light those up. We delay using FreeRTOS scheduler delays. We turn off the digit, and clear the segments and move to the next digit. And of course, there's only 4 digits, so we loop around. So that's this task. And then there's little helper functions here. And blinking has a big comment because I borrowed it, but it's very simple. So actually, I wanted to make sure I could identify the blink from the blink task instead of other blinks. So I made it a little more elaborate. It's on for 200 milliseconds. It's off for 50, so it's short. Its dark periods are short, and it does that 4 times, and then it waits with the light off for 600 milliseconds, and then it does 4 more blinks. So it keeps doing this. So it has this slightly unusual pattern, but that way I know for sure that it's not some other task that's blinking that I had lying around, which I did have. So, okay. So let's, at this point, I can stop the share and I can switch my camera to the hardware. And I'll turn this light off because then you can see the display better. And I'll pin myself. This was the trick in the video. And then I'm going to, you can't see it, but I'm going to upload, and I'll make sure you can see the lights, the upload lights. It's an off-board LED bit. Okay, so upload. It's not powered up, so that didn't work. Okay, now the board is on, and we will try that again. Needs a minute for the serial port to be recognized. Sometimes it helps to reset the board. Actually, it already has the code loaded, but I will load it again. Now it's uploading. And now it's counting. And this is actually, we saw this before last week, and it's working, but it's not very satisfying because there's a lot of flicker in the display. And that's visible, certainly visible in person, and it's visible on the video as well. So this was kind of problematic because, I guess I'll go back to screen share. Okay, so you don't have to watch that anymore. And there's a fundamental problem here. Within our scanning display scan, we're already delaying the minimum amount that we can, which is 1 tick. And as you recall, in FreeRTOS, 1 tick is 15 milliseconds, and 15 milliseconds is just too long. And furthermore, because of the way they implement FreeRTOS on the Arduino, they use a special timer called the watchdog timer, and the watchdog timer's, unfortunately, the fastest rate it can cause interrupts is 15 milliseconds. So therefore, we're stuck unless we wanted to really re-implement the port of FreeRTOS, which probably isn't actually that horrible, but it's we don't want to do it. So, and also it would not be the most friendly software out there, because it means we would have to take over one of the timers on the AT Mega, like probably one of the 8-bit timers. And yeah, there's several of them, but then the end user in the future is going to always have to know that they cannot use that particular timer. Whereas, the watchdog timer is used much more rarely. Okay, so what's the solution? So the solution is, let's put this task in an ISR very carefully. It's a little more elaborate than some of the ISRs we did before, but what if we wake it up, if we interrupt it we cause an interrupt every millisecond, which would be 15 interrupts per operating system tick, and we drive the segments using the ISR itself instead of a task. Then we should be able to scan this display just as fast as we did before when we used our own round robin scheduler with synchronization, and we had a 1 millisecond period. So yeah, so I actually frankly struggled with that for a long time, even though it looks like you just mouse the same code into an ISR, and I'll show you what happened. But instead of running this one further, I'm going to open another one where I saved it. Seven-segment FreeRTOS with ISR. And so what do we change here? Well, all of this stuff is the same. We're going to, we have a debugging LED, which helped me for the ISR problem. And I put in a little test. I'm going to make this faster. But basically, while we're still in setup here, and just to make sure, because I was so, why isn't that light lighting up? Because of that, I made it flash 3 times in setup to make sure the hardware was okay. So this means every time I was running, I never had the excuse, oh, the LED's not wired right. It's your software. Okay, so we're doing that. And this is stuff from before. We're just setting up all the bits that control the 7-segment display. They're DDRs, data direction registers. And we're clearing all the digits. The way this works is I think it's the cathode is the digit. Each digit is common cathode, and you drive the anodes to light the segments. And so to turn on a digit, you bring the cathode to 0. And so we have to set all these digits to 1 in order to turn them off. Okay, and then we have our 3 tasks. So we have our blink task, our display scanning task. This time I've turned it off because we're going to use an ISR instead. And then our task that counts, and it counts up. And then finally, we enable the interrupts. We set up the timer 4 to generate 1,000 interrupts per second. And again, these are functions that I wrote in order to talk to you about setting up timers without explicitly doing it for you. Okay. And then again, this counter is the same as we had before. It's going to count once per second now. And then we have our ISR. So actually, I'm going to turn on this test code. At first, I was just testing it to flash the light. So this is going to, we have a static volatile global called ISR count. Actually, this probably could be moved inside the ISR as a regular static. We'll try that in a minute, but I know this works. And then every time the ISR is finished, we increment the ISR count. And we use that to do timing relative to the ISR's rate instead of the operating system tick. So if ISR count is between 50 and 250, we're going to write a low bit. Oh, actually, I do not want to do that because it's either or. So I guess we'll turn off the display first. Okay, so the ISR, and that's actually not okay either, because that paren, that curly bracket is the end of the ISR. And this is old junk. Oops. This is old junk that I do not need. Okay. That's clearer. All right, so we commented out all this stuff, which is our new display driver. And so we just have this little test in the ISR. At 1 kilohertz, we're going to be looking at this ISR count between, for 200 milliseconds, between 50 and 250, we're going to write a low to the LED. And if it's greater, we're going to write a high and reset the ISR count. So we're going to have a 50 millisecond ISR light flash and then a 200 millisecond dark period, but no display on the LCD. So let's check this. It compiles and we'll upload it. But first I will switch, I'll stop share. I'll upload it. It's uploading. And okay, it blinked 3 times on the external. And now it is blinking, the blink task is running. But interestingly, our external the external test light is not working on the ISR. Why would that be? Shoot. How did that happen? Make sure I've got the brackets right. I do. You know, an annoying thing with the Arduino IDE is you upload and it does not save, and you have to remember to save. Sometimes you fix the last bug and it works and you think you're done.
Professor?
Okay, yeah.
Is it because you commented out ISR count ++?
Aha. See, there's always some smart person who helps me. So let's get this and back in. You know what? I knew it was, you're absolutely right. We'll check it. We'll upload again. And now it's working. Okay, so we get these quick flashes on the external light, totally driven by, thank you very much again, totally driven by the ISR. And this blink on the main board is driven by a task scheduled by the operating system. And so again, we'll go back to screen share. And we'll comment out the test code now. And enable the LCD display. But just to show you what's going on, okay, yeah. So now here, we've defined some pound defines for how many milliseconds or how many cycles will be on and off. So it's not that we're off for 4 cycles, it's that we start with 0. Well, we have states, and I actually am not using these states, but it just helps to read the code. So we get in here, if ISR count is equal to 0, we start the digit on state. We add update, if necessary, we wrap around the digit position. We light the correct digit. That's just the cathode for that segment, that digit. We figure out what digit, what what decimal number we're going to display in that digit. And then we figure out what segments it has, and we light up those segments. And then that's all we do at the first, when ISR count equals 0. Then if it's the digit on count, in this case it's 3, so 3 milliseconds later, we turn the digits off and we clear the segments. And finally, the digit off count is after the digit on count, so we really only go from 3 to 4 here. So only 1 millisecond, we will set the ISR count to 0, and then, to -1, and then increment it at the end. So when we start again with the next interrupt, we will start over. Okay, so that's how this is supposed to work. But I'm going to slow it down because I want you to see how that's working. So what we're going to do is make this more like 400. So it's going to actually, yeah, so it's going to be on for 3 milliseconds, but it's going to be off for 397 milliseconds. Hopefully we can still see it. Let's check it, and we will stop sharing and upload. Okay, and it is working. It's just scanning very slow. 7, 8, 9. In fact, it's scanning so slow that the counting task is going faster than the display. So maybe I overdid it. Let's cut that in half. Uploading again. And now 3, 4, 5, 6, 7, 6, 5 happened twice. It's definitely scanning too slow, and I did that on purpose. So now we'll go back to the numbers that I liked, 3 and 4. So it's on for 3 milliseconds and off for 1 millisecond, total of 4 milliseconds per digit. I'm going to save and upload again. 1, 2, 3, 4, and I don't know how it looks. Yeah, it looks on the video too. It looks rock solid. So it just looks like all the segments are on all the time because the human retina has fused those pulses into one DC light. So we're able to do something faster than RTOS can run by adding a little more complicated, slightly more complex ISR, which is equal to it's pretty much the same as what our task was, but we added some timing information. Any questions about that?
Professor, can you post that code in case we want to use the 7 segment in our lab 4?
Well, yeah, I will, because you've already done lab 3. So I will post some parts of it anyway. A lot of it depends on this exact, let's see, I'm going to go back to screen share. Before you, be careful what you wish for, because a lot of it is this magic right here. And this is very specific to the exact wiring that I used to wire my 7 segment to my breadboard and so forth. And so like, the segment G, I forget which segment G is pin 5 of my particular 7 segment display. And I put it into pin 47 of the mega board, and that works out to port L pin 2. And so then all this magic has to be here for the ports going into this array so that I could do things like just make a loop through all the segments. And so I will publish this code, but you will have to get this exactly right for your own wiring in order to make it work. So, okay. So that, yeah, I made up my mind. I will publish it. Okay. So that's that. And I wanted to also go through one more thing about FreeRTOS and some of the API features. So let's see. Okay, there's no more slides, but this is the, wait a minute, why can't I get this tab? Huh, interesting. Okay, I'm going to stop sharing, get the tab I want, and share again. Okay, so you should see a browser page on freertos.org. And the key thing is this API reference. So this is your guide to all the things that FreeRTOS can do for you once you re-engineer your tasks to work on our FreeRTOS, which is not that hard. Sometimes it's stripping complexity out of your task to do it. And basically, the whole idea is you just put your code into a while one loop so that it runs forever, and you pretend that none of the other tasks have to do anything. And that's where the preemption comes in from FreeRTOS. So we've already seen a bunch of X task create. You give it the pointer to your function. This is a function pointer, or really just the name of your function is the first parameter. That is not the name of the actual function reference that's in your code. And then this one is a string where you give it a useful name if you need a more friendly, user-friendly name. You give it some stack depth, and we can talk about that more. I have not found stack size problems yet with any of these things that you've seen me do. If you really give up, try making the stack bigger for a task if you're really unable to find what's wrong. Oh, I forgot to tell you what was wrong with that thing that took me so much head pounding to solve. And yeah, so anyway, it was here. So this, as you saw before, this is an interrupt vector pound define that's defined somewhere back there that is the comp A register equality bit in timer 5, and this is the vector for it. And this is not a good feature. If you compile this, it works. Now, let's say by mistake that I typed in timer 5 like that with mixed case. Then we compile it and check it. Come on, I don't want zoom there. It still compiles and there's no error. And I'm not exactly sure why this happens because that is an undefined symbol. I think I really honestly don't know why why it's allowed to not generate errors when this is an unknown pound define. So I looked at that over and over. It looked right, doesn't it? It looks right. Well, it isn't right because you have to have the right capitalization. So it also compiles with this. The difference is when this is all caps, it works. And when this isn't all caps, the interrupt vector was invalid. So the first time it got an interrupt, it just jumped off into some garbage and the program froze. Anyway, I did find it by comparing carefully older code that I knew worked with this code. And all right, now one thing that to lead in back to the RTOS API reference, what we're doing here is this ultra simple ISR where actually this is in a different example where we are just counting on a global volatile variable. And this is a good example of why we need to declare it volatile, which we do up here somewhere. And volatile means don't optimize compiler. And the reason is, suppose you're a compiler and you're trying to convert this into machine language. And you say, okay, increment counter. Well, that's cool, except this is dumb because nobody ever reads a counter in this function. And so I can just skip doing this and the program will run exactly the same. So that's actually incorrect because of the volatile or the volatile keyword prevents the compiler from that incorrect assumption. And okay, so at any rate, but this still uses a global, and that's not preferred. You probably have been penalized in other programming classes for using global variables. And so what we can do instead is send a message using this function with what's called a queue in FreeRTOS. We'll use the queue feature to send a message to whoever needs this information, and that'll be a little more formally correct. And also, it'll allow the operating system to, for example, suspend tasks that are waiting on that information. So anyway, we've seen examples of task creation, and let's look at queues. So a lot of options, but there's only a couple that we'll use frequently. And queue create, a queue is like a message buffer where your messages have a certain size. It can be very small, like an int, and the size of an int is 2 bytes. Or it could be, 512 bytes of data from a device or something. And then you have several of them in sort of a sequence, a first in, first out sequence. And this sets up the management of queues so that a task can put data into a queue for some other task, and the other task can read data from the same queue. And if there's no data in the queue, the task can be suspended automatically until data is present in the queue. So that's handy. Okay, so one example of that is going to be in our other FreeRTOS example, which I'll pull up. We'll open it. I guess I did this other example to try and get interrupts working, and I did it. Right. Okay, so this is the one we did with the blink task, and the blink task will, and with the LCD task, and in this one, the blink task, we also have a task called change blink, which switches the blinker from the board to the external LED back and forth. And we had 2 versions. Somehow I keep fixing that and it keeps going back to the old thing. Okay, and so first we did it with the operating system delays, and I guess I'll just, oops. Huh, what the heck? Let's see if that works. No. Okay, this must be some incorrect version. I am sorry about that. Okay. Can you guys see this Arduino window on the current screen share?
We don't see any screen share.
You do not see a screen share. All right, I'll fix that. Thank you. Okay, so this one, we have blink, change blink, and analog read and LCD. And let's build it. So how did I lose that library? Okay, why? Oh, I see why. I renamed it. That's my bad. I made a special version. I felt I had to do that. How about this? Okay, but that's because it's not importing the library, or it's not spelled right. Oh, that's better. Okay, so now we are going to upload that to just sort of remember what these tasks were. Okay, so this one is blinking alternately, and according to the thumbstick, there is a just different number displayed on the LCD. And okay, so I did make a more up-to-date version of this, which I will also show you now that I know how to fix it. And it builds, and I'm going to download it, upload it, and you'll see why. Okay, right, it's still working, and I just have a cooler display now because I can move this little bar graph, I can move this little asterisk around with the joystick, the thumbstick, and if I let it go, it comes back. And the actual A to D value is shown in the top row. Okay, fine. So what's going on here that's different? We will now share screen again. And let's look at the change blink task. The ISR is still this simple ISR. We're in version 1 of the change blink, so we're just but we're doing something different here. So first I'll show you in setup. We're going to build a queue. We're going to instantiate a queue. So this has two. It's 2 units long. It really probably could just be 1, and the size of the queue is just the size of an int. So these units are very small, and the queue is going to be called queue which LED. That's my name for it. And now when we get to task change blink, which is going to switch the LED pin between the board and the external periodically. So here's all we're doing. So we're saying the pin is equal to the LED off-board pin. And then we're going to add to the queue the pin. And I forget what the one is right now, I guess. And then this says send to back. What does that mean? What it means is that the queue is 2 positions long, and we're putting it at the input of the pin of the queue, not like cheating and putting it up at the front. I don't really like that name, but it's what they use. So it, in fact, we can read it. Here's queue create, but if we go back to queue management, queue send to back. I mean, it sounds like you're sending it to the back of the line, and in a way you are. And so it says put an item in the, post an item to the back of the queue, and it's physically copied into the queue. So that's of note. And then another task can take it from the queue in order that they're put in. So if you want them to be taken in the order that they're put in, you have to do send to back. Okay. So we're sending the pin number into the queue, and then we're delaying for 2 seconds. And then we change the pin to the onboard pin, and we send it into the queue again, and we delay again. So this is sending it back and forth. Okay, and we're still causing delay from the operating system, or measuring time from the operating system. And then the blink task over here is every time it's running in an infinite loop, it's checking the queue, and it gets a thing called the pin message. We say that we declare an integer pin message, and then we get a pointer to it each time, and we use that pin message to be the pin that we're going to set to be high. And we use that until the queue gives us new data. And what this is it means how long do we block waiting for new data? And we're going to set that to 0 because we want to check the queue, but keep working in our task. So exactly once in this 350 millisecond loop, we check the queue for a new pin assignment. So that's using the queues technique to do this communication in a better way than globals. Okay, right now, are there any questions about how we use the queue? Oops, that's my nostril cam. That's a better one. Any questions about using queues? And of course, you know, the details you got to get from this API reference. Okay, and we'll do one more thing, and that's to illustrate one more aspect of these. Many of these calls have a different form when you're in an ISR. You're not allowed to use the same call. And so send from ISR means we're in an ISR and we want to put something into a queue. And so that's going to be our last little mini micro project here. Let's, instead of using this count, and I haven't pre-tested this yet, but let's make another queue to send the ISR time to the time manager, but I'm going to do that in the other app that drives the LCDs.
So are you supposed to be sharing your screen right now?
Actually not yet, but I am about to. because I don't have the app up yet. All right, you should be seeing this, and this is the one where we have the 7-segment driver. Oh, but this one is not the ISR version. Yeah, this is the wrong one. Okay, and then I will get rid of that other one. Okay. So now what we're going to do is this time that we have the display scanning task off. We could even just delete it from this one. And we're using this ISR. And oh yeah, so what we're doing here is we have this deval, this D pointer, which is our global, that is the actual stuff to be displayed. And so let's continue to get rid of global variables. So we'll put that into the counter where it's actually being generated. Whoops. Okay, sorry about this. Where is my counting task? Here it is. Okay, so the D pointer is in here, and instead of just implicitly sending it, we're going to send it in a queue to the ISR. So that's actually backwards. We're going to the ISR. Okay, so first thing we have to do is set up a queue for that. And we'll do that in the same place as the other queue. We didn't even have a queue. Okay, then. So let's, I do not have this API memorized, so we're going to get the manual up. And we have to create the queue first. All right, then. And so then we will go back to the API, the IDE, and I can probably get those both up. Okay, that's better. All right. So we'll set up the queue. Okay, so this, as you recall, we're sending an array of 4 ints. I want to make sure that's really ints. And it might have been chars because we do not need them to be very big. But no, I used ints, okay? So because these digits are only between 0 and 9, I could use 8-bit bytes to save memory, but I'm not going to worry about that. So they're ints. Okay, fine. So that means that the size of an item in this queue is 4 ints. It's an array of 4 ints. And we have a name for this queue now. I'm going to experiment later and see if we can get to 1. Okay, so now whenever we count, whenever we increment in the task counter right here, we have to put the value into the queue. So send to back. And so we've now got a new D pointer, and we've got to xq send to back. And the parameters are the Q name, Q, I forgot what I called it, Q disk value. And the item is this pointer. And so it can be dptr because it's already a pointer. I think it has to, I think it has to be cast to void. But let's see if it doesn't. Let's see if we can get away with this. And then how many ticks are we going to wait after we send it? And the answer is 0 because we're already heading into a delay anyway. We don't need to wait. Okay, so the counter is putting values onto this tick. Let's make sure that compiles. No, something's wrong. D pointer was not declared in this scope, of course. Where is D pointer in the setup? Oh yeah, this was something I did to initialize it. We'll get rid of that. And Q display value is not, right, I have to give that a type. So just like the prototype, I have to say base type T, Q display value. So in your screen share, can you see both the Arduino IDE and the API reference document, or are you just seeing Arduino? Somebody?
You can see both.
Great. Okay. So I forgot that I had to initialize this with the base type. So let's see what that does. And XQ create, I must have spelled that wrong or something. Why is that not there? Huh. It's not finding, oh, I know. That requires a separate include for some reason. And we can see that in my other version, which has Qs. And I don't recall why that was the case. I think this will do it. No? Okay, let's try to make that a void. No. Okay, I'm going to look at my other one, and that should tell us. Huh. All right, I'm going to have to get back to you on that one. But we got Qs working on one of them. I think I keep confusing myself on which app has which features. And which ones I've changed. All right, I've just gotten beyond what I can manage here. So I'm not going to do that. But I'll get that back to you certainly Wednesday. So anyway, the point is to see how we're going to use these queues. We already did one of the queues that did work. And the main thing I wanted to get across here is that when you're, in this case, we're going to read from a queue in the ISR, you have to use the special ISR functions like message queue received from ISR. So when you're in, it's even inside the ISR, you're receiving from ISR. It doesn't mean you're getting it from an ISR. It means getting it in an ISR. Okay, I'm going to wind up there. And are there any more final questions or issues for today? Okay, good luck on 4.1, and I will see you guys on Wednesday.